Alright, so we're looking at the Unit 3 practice problem set. And just want to point out that you do have a full list of equations here at the beginning and solutions at the end. So let's take a look at problem number 1. An investor deposits $2,400 into an account paying an annual percentage rate, an APR, of 2.65% compounded continuously. Find a model that gives the account balance in dollars as a function of the number of years after the initial deposit. And then we'll answer a bunch of questions about that model. So we have an initial value of $2,400, an APR of 2.65%, and it's compounded continuously. So the appropriate model to use is right here. That is our continuously compounded interest model. So 2,400 times e to the 0.0265 t. This will be our model. And this is what we're going to use in all our computations. So we're going to input this model for y1, and then we can go ahead and do questions B through F. So off camera, I went ahead and entered the function in for y1, and now I'm going to look at part B, find the amount in the account after 5 years. That's a vars y vars question. So we want to evaluate the function at the input 5. And our answer would be $2,740.03. Let's go to question C. How long will it take, measured from the time of the initial deposit, for the balance to reach 3,000? So that's a type 2 question or a calc intersect question. So we want to know when the model will get to 3,000. I'm first going to go to my table. This will help me decide what my x max should be. And so I see here that I crossed 3,000 in year 9. So I'm going to go to my window, and I think I'll go up to, let's go to just a little bit above that. I went to 11, and then I'm going to do zoom fit. Alright, so we have our nice intersection. We'll go to second calc, intersect. First curve, second curve. And now we'll go to our guess. Hit enter a third time. And our intersection is going to be 8.42 years. Alright, part D, what is the account's doubling time? So if we start with 2,400, this is asking how long it takes to get to 4,800. And from there it's basically the same. I probably need to extend my window a bit. I could go to the table and see exactly how much to extend it. So I guess I'll do that. When do we get to 4,800? So it's going to take about 27 years. So I'll go to 30. Then I'll do calc, intersect, and looks like my picture is, oh, I forgot to press zoom fit. I think that's the problem. Sorry about that. There we go. So when I was graphing it, I just hit graph. I didn't hit zoom fit. And so you see why that's important, because I didn't get the intersection. Okay, so now I'll do calc intersect. Sorry about that. And we see our intersection point is 26.16 years. Whoops, and that was supposed to be down here. All right, part E. Find the account's effective annual yield. This is the EAY, and we have a formula for this, although it's actually not on this list. But actually this right here is the formula in a sense. We just have to write it for the EA in terms of the EAY. The EAY is E to the APR minus 1. And then if we want that in percent form, we multiply this by 100. So I'm going to pull up E to the X, and then for X I'll put in 0.0265. And then from that I'm going to subtract 1, multiply by 100, and we get 2.685. Now notice that this is very close to what our initial value was, just a little bit larger. That's what we expect. We expect it to be very close to our initial APR. Find the account's monthly growth rate. Okay, so notice that we have the APR, which is the annual percentage rate. So as I was saying, we want to find the monthly growth rate. So what do we begin with? Well, we start with the factor. So go to your model. Here's our original model. From that, I can pull this factor out. Let me actually pull up the whiteboard. So the annual factor is going to be E to the 0.0265. Now we need to take this and turn it into a monthly factor. And notice that I'm saying factor, not rate. And I know that this has an E in it, but this is not the annual standard or the annual continuous factor. It's just the annual factor. So the monthly factor is E to the 0.0265, and then that's raised to the 1/12. That's an exponent. Let me make sure that looks like an exponent. Okay, and that will be our monthly factor. And then from here we can go to the monthly rate. And basically we just need to take this value and subtract 1. So E to the 0.0265 to the 1/12, and then all of that has 1 taken away from it. And so let's run that computation. So that's 0.0265. And if you want to do it like this is fine. I can take that and then raise that to the 1/12. There's a lot of ways to input this. And it's 1/12 because we're going from yearly to monthly. Now that's the monthly factor. Then I subtract 1, and I have the monthly rate, and in percent form, that is 0.221%. So that will be 0.221%. Oh, and I was supposed to go to 4 decimal places, which I did not. So that would be 0.2211%. Okay. All right, let's move on to number 2. In the following table, y is a function of x. Is the function linear, exponential, or logarithmic? All right, so we need to decide what kind of data we're looking at. The first thing that I'm going to do is I'm going to type all this data in my calculator and do a stat plot and look at it. So I'm going to do that off camera, so I'll pause for a moment. Okay, so I just went to my stat editor and entered all this data. And now I'm going to do a stat plot. So I go to second, y equals, my stat plot was already turned on, so check and make sure yours is turned on as well. And then you should turn it off after we're done with this. So then go to zoom, and we're going to do a zoom stat. Alright, so there's my data. Now to me, that obviously that's decreasing, but it also looks like it's concave up. So it looks kind of like this, right? So I would say that is not going to be linear. So I think I can safely rule out linear. That could be exponential. So yeah, that could be exponential, but it could also be logarithmic. So really we're going to have to just look at both of them and decide. And one thing I can do is I can compare the SSEs of the regression functions. So let's try that. Oops. So I'll do stat calc expreg L1 L2 vars y vars function y1. So there's my regression function, and the SSE is sum resid squared. It's 27. Okay, well, that's pretty low. Let's check the logarithmic. So to do this, I'm going to have to, since I'm comparing functions, I'm going to have to do, this one is y2. So I do ln reg, not ln reg, but ln reg of L1, L2, sorry, L2, and remember what I said, that one's going to be y2. And then we'll do sum resid squared of that one. Okay, now this is a very small number, 0.00001, much smaller than the other SSE. So it looks like the natural, or the logarithmic regression is the one that we want. That's the exponential regression, the first one coming through. And that is the logarithmic. So the logarithmic is a much better fit. So we're going to do the logarithmic regression. So to find f of 13, which is question B, we need to be careful here because I've got y2. I need to remember that y2 is my function, not y1. So y2 is the logarithmic function, and I want to know its value at 13. And that is negative 1.25. All right, great. Number 3, in the following table, y is a function of x, and we basically have the same question, so we need to do the same thing. We need to graph this data and pretty much attack it the same way we did number 2. So I'm going to enter this data off camera. Alright, so I've entered the data, and now I'm going to do a stat plot. So I'll do zoom stat. And there's my data. So in this case, oh, and there's a function left over, so I don't need that anymore, but ignore those two lines. Sorry about that. Alright, let's go back to the graph. So in this case, I'm not really sure. That to me looks like it's a little bit concave up, but arguable, I suppose. So I really think I might actually just go ahead and check all 3 of them, which we will do in the next video.